In Chapter 14, Section 3, we learned to describe simple harmonic motion. As we learned previously in the chapter, simple harmonic motion describes a quantity that oscillates in time, passing through its point of equilibrium repetitively, and is characterized by a sinusoidal-shaped graph. Sinusoidal functions can be written as a sine function, where x equals 0 at time equals 0, or a cosine function, where x equals the max or minimum amplitude at time equals 0. To be a sinusoidal function, the value of x has two limitations. It is bounded between a maximum and minimum value of amplitude a and negative a, and the value of x must be periodic, meaning the x values are repeated over and over in equal time intervals. Sinusoidal functions can describe the position, velocity, and acceleration of an object traveling in simple harmonic motion. Position is a cosine function, velocity is a sine function, and acceleration is an inverse cosine function. We will use these equations to describe the motion of the bike wheel as simple harmonic motion. Looking at snapshots from the video of the bicycle wheel, we can determine what sinusoidal function to use and determine whether uniform circular motion can be described as simple harmonic motion. The radius of the bicycle wheel is 13 inches. For easy computation, we will use this position of x equals 13 at time equals 0. On a unit circle, this point equals 0 and 2 pi. Period t equals the time it takes to complete one full cycle, or 2 pi. So at this point, t equals 0, and after one full cycle, t equals period t. Rotating the wheel counterclockwise a quarter cycle or 90 degrees from the start position, x equals 0, and time t equals 1/4 period t. Continuing rotation a half cycle from the start position, or 180 degrees, x equals negative 13, and time t equals 1/2 period t. Rotating the wheel counterclockwise 3/4 of a cycle, or 270 degrees, x equals 0, and time t equals 3/4 of period t. Taking into account the limitations of a sinusoidal function, the rotation of the wheel is bounded by a maximum and minimum value of amplitude equals 13 and negative 13 respectively. As the wheel is traveling in uniform motion, we can see that the values of x are periodic, passing the same x values in equal time intervals. Timing the wheel rotation in slow motion, it took the wheel 5 seconds to rotate a complete cycle. This defines the period t of this motion as 5 seconds and the frequency to be 0.2 Hz, or 1 cycle every 5 seconds of uniform motion. We will be using the values defined in the pictures to show how uniform circular motion, when projected onto one dimension using the x component of position, velocity, and acceleration, describes simple harmonic motion. To form a position versus time graph, we will use the cosine function x of t equals amplitude times cosine of 2 pi times time t over period t. This equation is derived from the equation for finding the x component of a position on a circle, where x equals radius times cosine of theta. In uniform circular motion, theta is the angular velocity times time. Angular velocity equals 2 pi times frequency, or 2 pi over period t. A cosine graph was able to be made from 5 known values listed in the position versus time table that were defined in the snapshots of the wheel rotation. From the graph below, we can conclude that the position versus time function is a cosine function because the cosine of t equals 0 is 1, which would make x equal the amplitude. With this information, we can find any position x at any time t. The question below asks what will be the position of the tape at t equals 3 seconds. Plugging in 3 seconds for time, 13 for amplitude, and 5 seconds for period t, we can calculate the position x to be negative 10.5 inches. Remember that the velocity vector of a circle is tangent to the circle. If a circle is moving counterclockwise, the x component of the velocity vector is pointing in the negative direction when the y component is positive, and in the positive direction when the y component is negative. To create a velocity versus time graph, we will be using the equation x component of velocity equals negative 2 pi times frequency times the amplitude times sine of 2 pi times the frequency times the time. Velocity max is calculated by the equation velocity max equals 2 pi times the frequency times the amplitude. Using the cosine function with the known time intervals, we were able to make a velocity versus time table. The velocity max equals 16.34 meters per second, which is the maximum and minimum values in the graph. The velocity is initially negative because the x component of the velocity vector points in a negative direction. The circle below is just a quick sketch of velocity vectors in each quadrant showing the direction of the x component of the vector. The question below asks, what is the velocity of the wheel at t equals 3 seconds? Plugging in 3 seconds for time and 0.20 for frequency, the velocity at 3 seconds equals 9.6 meters per second. Finally, we can create an acceleration graph to describe the simple harmonic motion of the bicycle wheel. Centripetal acceleration in uniform circular motion always points to the center of the circle. We can determine the x component of the centripetal acceleration by x component of acceleration equals negative 2 pi times frequency squared times amplitude times cosine of 2 pi times frequency times time. The max acceleration is found by multiplying 2 pi times frequency squared times amplitude. As you can see by the graph, acceleration is an inverse cosine function created by using the values in the acceleration versus time table. Max acceleration equals 20.5 meters per second squared. This is the max positive and negative value of the graph. The question asks, what is the acceleration at time equals 3 seconds? Putting in 3 seconds for time and 0.20 hertz for frequency, the acceleration at 3 seconds equals 16.6 meters per second squared. By using the functions for position, velocity, and acceleration to create graphs of the circular motion of the bicycle wheel, we were able to show that uniform circular motion using the x component is in fact simple harmonic motion.